whenever we're doing integration by hand, we want to say that we're undoing differentiation, or we're doing the opposite of differentiation is the best way to think about it. So this first problem here says, consider the area under the graph f of t equals 3. And it's got this picture of the graph drawn to the right. And it says between t equals a and t equals x, where a is less than x. And it says show that the area function a of x is equal to 3x minus 3a. So what happens is when we do an integral, like you want to say integral from a to x of, we'll say f of t dt. It means when you're doing that, you're going to come up with some like f of x. Like we use a capital to represent the integral, capital letter. So we'll just say f of x here. So in this case, it was 3. So we'll just write down 3 dx equals the capital F of x. And the way you want to think about, like I said, undoing integration, or undoing a derivative, basically, because 3 is a derivative. We'd want to do, like, before, if we were doing a derivative, let's just take an example here. If I did 3x squared plus 2x plus 5, something like that. And I said, let's take the derivative of that. We would say 3 times 2, x to the first, plus 2 times 1, x to the 0, plus 5 times 0, x to the negative 1. And that would simplify to 6x plus 2. And then everything else would kind of go away. That's how we talked about doing derivatives before. Now, if I wanted to integrate that, instead of multiplying by 2, what I would do is I would divide by 2. I'd say 6 divided by 2, and then I would put a 2 up here in the integral. So when I'm adding a number to an exponent, I want to divide by that number in the lower part. So this would be 2 divided by 1, x to the first power. That's how I would undo an integral, or a derivative. So again, it was divide by 2, so I'd do 2 to the first power. Divide by 1, so I do x to the first power. Or I do x to the second power over there and x to the first power here. That's the idea here. For whenever we're undoing a derivative, the best way to think about it is we want to divide instead of multiply by that number that we're putting back up into the exponent. So the same thing happens here. The derivative was a positive 3. So in order to undo a positive 3, we would say 3 divided by 1 times x to the first power, or just 3x. That's what the f of x function would be here. Okay, so whenever you do area of a, I did not leave us a lot of room here. So that's how we would find an integral. I'm going to erase this part over here. Kind of useless right now. So whenever we do an integral, we find, let's see, the next part. There we go. We'll try this again. It goes from a to x, and we said 3 dx. So what happens is we would write down a bar that kind of goes backwards like this, like a backwards bracket, and we put an a and an x on it, and then now we say 3x. So we found the integral. We undid the 3 by dividing by 1 and then doing x to the first power. And that's what this looks like. And then in order to calculate the area, which is what this part's saying up here, you actually substitute in the two values. In this case, the values are x and a. So we would say 3 times x, and then subtract 3 times a. You do the first one, the top upper bound, minus the lower bound. And the way this works actually is, I might have to scroll to the right here to show you a little bit better. So we have this y-axis here. That's kind of like our boundary. And what happens is when you say, I'm looking for the area under a curve, like let's say t to the x, it's going to say, okay, I'm going to find all of this area here, all the way back to the y-axis. That's below the line we had. In this case, the line was t equals 3. As we can tell, when I'm looking for that whole area, which is just evaluating this x right here, I'm including a big part right here that I don't want included. So how do I get rid of that part? I have to do a little subtraction. And that subtraction is the minus 3a, because when I do t equals a, it's going to take everything from here over, and it's going to subtract that part out. That's the whole idea with integration, is when I'm doing a 3x minus 3a, that's exactly what's happening. I'm taking the whole thing all the way back to the y-axis, and then I'm subtracting just the second part. It gets a little bit trickier when we get into negative territory, so we're not going to look at that example right now. But that's kind of the idea, and that's where you come up with this part where you say, okay, I have to do the whole area all the way back to the y-axis, and then, oh wait, I have to subtract the other area, and then that's just going to give me the area in the middle that I want. That's what this whole equation is saying right here. The ax equals 3x minus 3a. So we're going to see a couple different terms today. We're going to see f of x, which basically means the integral. And then we're going to see a of x, which is the area of the integral. So those are some new things we'll see today. We'll see a capital F of x and an area a of x. And so it actually talks about it up here. A of x is the integral of f of t. So I did write this improperly. This should have been a 3 dt right there, and then this should be a 3t, and then we plug in x and a for that t. So I wrote that a little improperly, and if we were just doing f of x, it would just be 3x. That's the difference between f of x and a of x. Sorry, it's been a while since I've done this myself, so I apologize if I mess up the notation a little bit while I'm doing it. Alright, so that's what like problem 1 looks like there. Problem 2 here is going to give us a different problem.
What's the final answer for that one?
The final answer for this one, sorry. It's a show that problem, so it's saying, hey, show that the area of the function is this ax equals 3x minus 3a. And I was just trying to explain where it came from, that's all. Sorry, I did not do a great job of explaining where it came from. But let's take a look at another one, and we'll see if it makes a little bit more sense the second time. So this time, we're going to look at this function. Instead, the first one was f of t equals 3. So it was a constant term, straight line. Second one, f of t equals t. So if I were to graph this, and say this is my f of t, or my y-axis, and this is my t-axis, we're going to draw a straight line, linear function, that's just going straight up, right? The slope is 1, f of t. f of t equals t. Okay. And then, again, you're going to do between t equals a and t equals x. And we're looking for this area here. So this is kind of what problem 2 is asking us to do. Go ahead and sketch the function and then sketch a picture of it, of what area we're looking for here. And this is where a is less than x. We already did that. Now it's giving us another show that. Show that the area of this function is x squared over 2 minus a squared over 2. So we'll want to again draw an integral. This time it's t. So t is just simply the function, right? It's always area of x equals the integral of f of t, and in this case f of t equals t, so I'm just substituting it in there of that. And now I'm going to ask you guys to see if you can figure out what the integral is by hand here. Figure out what t is going to be by hand. What's it going to look like? And that's the first part. So it starts with the t to the first power. So we're doing an integral, so I can guarantee it's going to end as t to the second power. So we're going to need to divide by something. What are we going to divide by? That's the trick for these types of problems. Kind of weird. So it should be t squared over 2. And if that gets confusing for you, which I understand completely if it is, this was totally confusing for me in high school when I was trying to learn calculus. What happens here, think about taking the derivative of this. You would write that as 2 times t to the first divided by 2. The 2's would divide out and you're left with just t to the first, which is just t. It's just perfect. That means I did it right. I'm just undoing the integral. I'm double checking my answer basically by taking the derivative. Perfect. So now I've got this xa and then t squared over 2. And the next part is to substitute in. I need to start by saying let's substitute x first. Because if I substitute x, that means I'm taking the area of this entire triangle. So x squared over 2. And then next part I'm going to substitute a. And if I substitute a in, I'm taking the area of this small triangle here. And I don't want the area of that small triangle, that's why I'm doing the minus part. I need to subtract that part out. And I get x squared over 2 minus a squared over 2. All right. Hopefully I explained that one a little bit better. So second try, a little bit better. That's the goal. But that's the idea for these types of problems. Whenever you're talking about an area function, you're ended up doing the upper bound, and that's going to go all the way back to the y-axis, and then you do minus the lower bound, which is also going all the way back to the lower axis, the entire axis. And the stuff that's left over should be just the stuff in the middle here. So this equation should theoretically represent just the stuff in the middle when we do the subtraction. Okay, that's the idea. And then we take the integral of it, and the integral of 2t should be 2t squared over 2. We have to divide by 2 when we're raising this to the second power, and then the 2's will actually go away, so we're just going to be left with like a t squared. Which makes sense because it says we're looking for an x squared minus a squared. So then when we substitute it in, we're going to do an x squared for the first part minus an a squared for the second part. And again, the x squared represents this first part of the area, which would be all the way back to the y-axis. The a squared represents the second part of the area all the way back to the x-axis. Okay?
Where do you get the square and divided by 2 from?
Where do I get the what? The square and the divided by 2? Okay, that's when we're taking the actual integral. So what happens is when we do a derivative, remember when we would, let's say if I just had a 3x squared plus 6x or something like that, or actually we'll just say, let's just say we have an x squared plus 2x, something simple. When you take the derivative, remember we would do 2 times x, and then this one would be 2 times 1 times x to the 0. So that's where the derivative came from. So when we're doing an integral, you actually do the exact opposite. So if I have 2x plus 2, which is right here, and I want to take the integral of that, which means I want to get back to this step right here, I would say I need to do division instead of multiplication. So I'm going to divide both the numerator and denominator by 2, and the squared goes in because I'm doing the division. And then here I would divide by 1 and then put next to the first power in. And then what happens is I get 2 divided by 2 becomes x squared. 2 divided by 1 is just 2. And I get x squared plus 2x. And it turns out that gets me back to where I was before. So an integral is undoing a derivative. So that's why we're doing the opposite of what we would do for a derivative. So derivatives, we always multiply by whatever the exponent was. In derivatives, in integrals, we divide by that exponent. Okay, that's where this part comes from over here. I hope that explains it a little better. And that's where we end up getting the show that part at the end there. Okay, now, so for part 4 here, it says the results from 1 to 3 are summarized in the first 2 columns. All right, so we had the function was f of t equals something. So the first one was f t equals 3. Second was f of t equals t. Third one was f t equals 2t. The expression for a to the x have been written as difference between 2 terms. The first term is a function of x, and the second term is a constant. So what happens is in most derivatives, we're going to give you a constant for the lower limit, or the constant could be the upper limit as well. And then the other one's going to be a variable that changes. So it depends on how much area we're asking you to look for. So this one says, what do the 2 terms have in common? So what do these, basically it's asking what's the first term have in common with the second term? What's the first, let's do that in different colors. So what's this term, the first term, have in common with its relative second term? That's what we want to talk about in this first part. So what do you think they have in common? Any thoughts?
Like they match the same process. It's like it's 3 times x and 3 times a. And then it's x squared over 2, a squared over 2. It's like it follows the same process on each one.
Exactly. So they've matched the process. It can get really tricky when we're not dealing with a variable there for the second one, like a, because if it was just a constant, if it was just like the number 2, you'd have 3x minus 6, and you would say, I don't know what the relationship is. For the second one, it'd be like, if it was a 2, it'd be 4 over 2, so it'd be like x squared over 2 minus 2. And again, you're like, I don't know what that relationship is. So yeah, it's the same, they follow the same process to calculate. All right, you're going to plug in whatever that constant term is. In this case, it's just being held by a variable a. But yeah, in in practicality, it's always going to be a constant term. So they're following the same process. If the first one's times 3, the second one's also going to be times 3. If the first one's squared divided by 2, the second one's also going to be squared divided by 2. Alright? Now it says, let the first term in each of the expressions of a of x, for a of x, be the new function f of x. See, so I was jumping the gun a little bit when I was explaining this earlier. So the first term is f of x. So we want to complete the third columns here. Oops. With just the f of x functions. So f of x in this case is going to be x squared over 2. F of x in the third case is going to be x squared. Okay, it says, for which value of a are the expressions for f of x and a of x equal? So, what does a have to equal to make? What does a have to equal? Lowercase a have to equal to make this equal to that. So what does a have to be to make 3x minus 3a equal 3x? It's kind of a weird question, but just think about it for a second. So let me ask it again a different way. We have 3x minus 3a. And I said, well, what happens if that's the same thing as 3x? We have 3x minus 3a equals 3x. What does a have to equal? Like, what happens if I subtract 3x from both sides? What's 3x minus 3x? 0. What's 0 divided by negative 3? 0. So what does a equal to get us to just 3x? A equals 0. And that makes sense, because if I did 3x minus 0, I would end up with 3x. If I did x squared over 2 minus 0, I'd end up with x squared over 2. If I did x squared minus 0, I'd end up with x squared. So that's what this one's asking us for. Okay. So this one's asking, so a equals 0. So now what area would be represented by f of x when a takes this value? So that would be, like I said, if you're doing the area of just the first part, you're doing the area all the way back to the axes. So that's the area that's represented. Okay, that's kind of what this question's asking us about here. So it's the area all the way back to the axes. To the y-axis. And then how would you represent this area using definite integrals? So we would say f of x equals the integral from 0 to x of f of x dx. So it's just saying we would go from 0. 0 would be our constant term, not a. That's kind of what that question's asking us to do. Yeah, I was looking at this. This was an investigation in your textbook, which they're supposed to be usually student-led, but I can see this one being really confusing since we haven't talked too much about these integrals yet. So that's the idea for this problem. That's why I'm kind of leading you guys through it a little bit more today. But that's the idea there. Okay, now, the last part says, complete the fourth column on the table by writing a of x in terms of f of x. The first row has been completed for you. So you're writing a of x in terms of f of x. And for this one, hopefully we see a pattern. It should be the same for all of them. F of x minus f of a. F of x minus f of a. Doesn't matter what the second term is, we're always going to be doing the first one minus the second one. That's kind of the goal of that. Just that we're seeing that's going to be the exact same process every single time when we're looking for an area and an integral here. Okay. Now, the last one here is going to ask about slopes. So what's the gradient of the graph f at every x? But notice it's the capital F, not the lowercase f. So it's saying, here's two graphs. It says below are the graph shown of f of t, the lowercase f, equals 3, and then uppercase f of x equals 3x. So what's the gradient of the graph of f at every x? So basically it's asking, what's the slope in the blue graph, the graph on the right? What's the slope? And then how does that relate to the other graph, the red graph? So starting with this graph on the right, what's the slope of this graph if you have f of x equals 3x? Anyone know what the slope is? Or the gradient?
3.
Yeah, exactly. Slope is 3. How does that relate to the second graph? What's the 3 have to do with the other graph? It's just the constant, right? Because the second one has a slope of 0, but it's just at 3 the whole time. Okay, that's kind of the idea. And so the whole idea here is whenever we were taking a derivative before, we use the derivative to find the slope at a current point on the function. Okay? And that's kind of what this is relating to here, is it's saying, hey, the graph of lowercase f of t here, this is representing the graph of the slope of the function over here. The slope happens to be 3, so it's just a graph of 3 because it's a constant slope. Kind of a weird way to explain that, but that's what's going on. So whenever we look at the graph of a derivative, the graph of a derivative is always the graph of the slope. All right, we never really hit that hard in chapter 12 with the graphing part specifically, but that's kind of what this is trying to bring it to, is bring it all together why we're doing integrals, because we're going back the other way. We're looking at slopes and things like that. Okay, so for each of the two remaining functions f, find an expression for the gradient of the function f at every x. What can you say about the relationship between the gradient function of f and the function f? So that's saying for the other two problems we did, one of them was f of t equals t, and the other one was f of t equals 2t. What was the corresponding f of x for each of these? And then what's the relationship between slope? All right, so what can you say about the relationship between the gradient of the big F and the function f? That's kind of what we're trying to look at here. So I want you guys to graph them. You can look at them in Desmos if you want. You can look at them, our little sketches of the graphs, whatever helps you do it. But you're gonna need to graph. You're gonna need to graph these functions here, which this one was x squared over 2, and this one was just x squared. All right. So maybe it'll help you if you graph them. But what's the relationship between slope and its corresponding other graph? So I don't know the best way to use my words to describe that. So
left a little bit.
Yep. Sorry. There you go. So yeah, you might want to graph one like f of x equals x, and then graph f of x equals x squared over 2, and compare them that way. That might be a good way to do it. But just take a minute to look at them. Now, for example 12, it says consider the definite integral 0 to x 3 minus 2t dt, where 0 is less than or equal to x is less than or equal to 1.5. And it says draw a diagram of the function f of t 3 minus 2t and shade the area represented. So first we want to draw a picture of it. And then second, we're going to use antiderivatives to find the expression. All right, so go ahead and see if you can work on example 12, draw a diagram, and then find the antiderivative for the second part. See if you can do that part. Give you about 5 minutes. This problem. So the first one, just sketching the graph, f of t, so draw a diagram of it, and then shade the area represented by the integral. So we can just put t equals x anywhere we want, as long as it's inside the function, and then we just shade the area for that part. So your drawing could look a little different than mine, that's perfectly fine. But yeah, you just put t equals x anywhere you want, as long as it's inside that function, and you're capturing all the way back to 0, since it's going from 0 to x. And then we do the antiderivative. So I went ahead and said capital F of x equals, and I wrote the whole derivative down, and then I found the integral of it, which is 3t minus 2t squared over 2, and the 2's would divide out, and then I substituted in the x, and I got 3x minus x squared, because if I substitute the x in, I get this. If I substitute the 0 in, it's just going to be minus 0, so I didn't need to write that second part. So that's how I ended up with the 3x minus x squared. I skipped the second part because it would have just been minus 0. So there was nothing to write there for the second part, if that makes sense. Okay. Any questions on examples 11 or 12 before we move on? So examples 11 and 12, that's...
I don't know how to ask about it.
Yeah, what's up?
I said yes, but I don't know how to ask about it because I'm not really sure,
Sure.
what it is I don't exactly get.
Okay. Yeah, we'll try and answer your question at the end of class then, if we can. So that's going to cover like section 13.f in the textbook when you're doing your assignments. And then the last part I want to talk about today is what's called an indefinite integral. And the only difference between a definite integral and an indefinite integral is the indefinite integral doesn't have any limits. There's no upper bound, there's no lower bound. All right, it's just the integral of f with respect to x. And I've mentioned this a little bit before, but we say you're going to do f of x plus c. C stands for a constant. So when you're doing an indefinite integral, you always add the constant in to represent that there could have been a value there before. So this one says find the family of antiderivatives of f of x equals 5. Basically, it's just asking you find the antiderivative of 5. So you just do the derivative of 5 dx. And this is going to equal what's called f of x plus c. And what we do is to take the antiderivative of 5, you're going to get 5x, and then plus c, and you just say where c is all real numbers, an element of all real numbers. Just c could be any number. We don't know what number it is, but remember whenever we took derivatives, you always had a constant term that just went away. So that's what the C is representing. It's representing that constant term that went away when you took a derivative before, like in chapter 12. Now we're representing it differently. That's the only difference between indefinite integrals and definite integrals is in the indefinite integrals, you're going to need to put this plus C in there. And you're going to need to state that it's all real numbers. Okay? Only difference between indefinite integrals and definite integrals. And you can tell the difference because indefinite integrals don't have any bounds. There's no numbers written next to that little integral symbol. The last one here says find the integral of 4x. So you do 4x squared divided by 2 plus c. And then simplify. So 4 divided by 2 is 2. So you're going to get something like 2x squared plus c, where c is an element of all real numbers. That's how you would write problem 13. Okay. So you're just doing these antiderivatives, and you're just dividing by the exponent instead of multiplying by the exponent. That's the difference between derivatives and antiderivatives.